k. Okay, it's not a square. N squared plus m is not a square. And here's my proof. N squared plus m is strictly greater than n squared. How come? Because m is at least as big as 1. So it can't be equal to n squared because it's bigger. And I'm going to also claim that it's strictly less than n plus 1 squared. So it can't be a square because it's stuck in between two squares. Who does that song, Stuck in the Middle with You? Is it the Eagles?
No.
Don't think so.
No, it's not, right? Doesn't matter. Here we are, stuck in the middle of these two squares, and this is bigger than this one, and it's got to be smaller than that one. This part is true because m is bigger than or equal to 1. Why is this part true? This is n squared plus 2n plus 1, and m is definitely less than or equal to n, so it's certainly strictly less than 2n plus 1. Therefore, this is true. Therefore, I conclude n squared plus m is between two squares. It can't possibly be a square. I write a little English paragraph. I say QED. I'm all done. It's a lot of work, but it's a powerful tool, and the idea of it is very straightforward. Clicking? Good. All right. And you'll notice, well, what trick do you use? Like here we picked 2, and the trick was that it was in between two squares. Before, we wanted to pump up a part to make it not look like a palindrome. And if you're thinking, boy, is it always something different every time? Yes, it's always something different every time. And yes, you have to look in advance, and the best way for a beginner to try is try something, let the opponent work as hard as they want, see if the opponent wins, and go back and fix your try if it didn't work. And when you get better and better, you'll be better at picking it in advance. And if you can't get it after a couple tries, ask me and I'll tell you. That's always a good way. Okay. Questions about this?
And we know it'll work because the problem says use this because it can't be right. But you could be sitting here and at some point go, well, maybe it really is a regular set.
Right. We're going to do that. No, maybe it really is a regular set, or maybe it really has the pumping property. Even worse, maybe it really has the pumping property and it's not a regular set. So I could sit here all day long and never succeed with this, even though the set happens not to be regular. And that happens. We're going to do an example in just a second. Okay, can I erase this one? Let's do another example. What about all numbers that are not prime numbers, that are composite numbers? Now, in doing this, we can go through that, the same kind of thing. Let's say somebody picks an n. I don't know how many states that is. Maybe their machine has a prime number of states. Maybe it has a composite number of states. Whatever number they pick, what if I just pick 0 to the 2n? I know that's composite. I know it's bigger than the number of symbols they have in their machine, so I'll try this. Everybody with me so far? So this is my z. And the opponent, I'm not writing it out informally this time. I want to just make more sense out of it. So the opponent splits this into 3 parts, VWX. The W part's got to be somewhere in the first n symbols. Now you're the opponent. Nail me down so that no matter what I choose, this is going to end up staying composite. That would make it hard for me. What W do you want to pick? Or we can turn the board around. I'll be the opponent. You be this guy. In a second, I'm going to be trying to taking the 0 to the 2n and then adding multiples of this W to it and hoping to get something that ends up being prime, that ends up being not composite. How am I going to do that if you make this W equal to 2? 2 zeros. If you make the w equal to 2 zeros, then I'm always adding 2 zeros to it. 2 zeros to some even number. I'm always going to get an even number. I'm never going to get a prime number. I can pump up w to my heart's content. I'll still get an even number. The answer is that I'll never succeed, and you'll kill me if you pick w equal 2 zeros. And I can't pick a better string because you can always just find w equal 2 zeros. Maybe I should have picked 3. Well, then you could pick w equal to 3 zeros. Whatever I do, you're going to nail me in the next step. We could play this game a lot, and I would lose every time. And in fact, if you go back and do it the forward way, you can prove that 0 to the k, where k is composite, that it does obey the pumping property. You can always find some little part in there which you can pump up and keep getting composite numbers. But this is not a regular set. So here's an example of something where the pumping property happens to hold. That means I'll never succeed in showing it's not regular using the pumping property. The pumping property happens to hold, but it's still not regular. So you give up, but you still have to show that it's not regular. So there's a related technique which is very easy to do. Let's say I already showed to you, because you're going to do it on the homework, that the complement of this is not regular. On the homework, you can use the pumping lemma to show that 0 to a prime is not regular. You can get a hold on that. It would take me 20 minutes to go through the answer, and maybe we'll do it as a review, but I want you to try that one on your own. It's a homework problem. You will do it. You'll use the pumping lemma. You will show that 0 to a prime is not regular, and you're done. Now, when you're done doing that, how do you then conclude that 0 to the composite is not regular? Not by using the pumping lemma again, because it wouldn't work, but by noting that these are complements of one another. So if this was regular, then that would have to be regular also. Therefore, it's impossible for this to be regular. Does everyone get that idea? That's the idea of closure. If you know that regular sets are closed under complement, and you know that the complement of the set you're dealing with is not regular, then the set you're dealing with is also not regular. If I know that 0 to the prime is not regular, and I'm not sure about 0 to the composite, and the pumping lemma isn't working, then I can say, well, I know it can't be regular anyhow, because if it was regular, its complement would have to be regular too, and I showed before that its complement wasn't regular. So it's kind of a proof by contradiction using closure properties. And you can do this with complement or reverse or any of the closure operations. It expands the repertoire of what you can show is not regular by a lot. So closure is not only used in a positive way, it can be used here in kind of a negative way to show that things aren't regular sets. All right, questions about that idea? What's another good example of this? Here. We showed yesterday that 0 to the n, 1 to the n was not regular. Right? We used the pumping lemma to show that. We could do it again formally today. Let's assume we know that that's not regular. How would you show that an equal number of zeros and ones are not regular? That means mix them up all you want, but there have to be an equal number of zeros and an equal number of ones. They don't have to come first zeros and first ones. Well, actually, you could do that with a pumping lemma, and it wouldn't be too bad to do it. But you could also do it with this trick. Equal zeros and ones intersected with 0 star 1 star equals this. Does everyone agree? If you take all the strings that have an equal number of zeros and ones, and all the strings that start with zeros and end with ones, and you say, what do they have in common? They have these in common. The strings that start with zeros, ends with ones, and have an equal number of zeros and ones. This equals this. But are regular sets closed under intersection? They should be. They are. Therefore, you know this is regular. You know that's not regular. So what are the choices for this guy? Not regular. If this one were regular, then the intersection of the two would have to be regular. Everyone understand that? It's the same idea. Here we're using closure over intersection. It gives you a tremendous variety of ways to show things are not regular. The pumping lemma is a direct way, and then these closure properties is an indirect way. Keep in mind, here it's really not necessary. If somebody wants to show that equal zeros and ones are not regular, I can just come up with a string of equal zeros and ones. Here, 0 to the n, 1 to the n. That's the string I pick. And then I'll win the argument just like I did with 0 to the n, 1 to the n. And that's kind of the intuition behind what Chris was saying the other day about, oh, if we